Up here are measurements, our scientific notation, everybody's favorite thing, our significant figures, conversions, temperature conversions as well, just in case. We'll do a little bit of density, perhaps, as we go through it. All right, so let's just start with really the basics, which hopefully you know, but obviously when we take any type of measurement, you always want to make sure you have both a number and a unit, right? And those two things are really important because if you just say something like 155, who knows what I am talking about, right? So maybe it's $155, which would be great. Maybe it's 155 apples, which might still be great, depending on your perspective. So this number really has no meaning if there's no unit associated with it. So, maybe it's 155 grams. So we should always have units associated with numbers and measurements that we take. It lets people obviously understand what those values represent. When we talk about units, as you may be familiar with, there's kind of two major types of units that we come across. One's the English system, and sometimes referred to as the US system, which is what we use here. Then pretty much everybody else in the world there uses the metric system. And as you can imagine, if everybody's sort of using different units, it can get a little confusing. So believe it or not, in 1960, they had a conference on weights and measures. Sounds like a lot of fun. And basically, they came up with sort of a standardized system of units that's oftentimes used in chemistry and other sort of sciences, which is sometimes referred to as the SI unit, which is the International System of Units. And we have basic units of like length, for example, which is like the meter. We have things like mass, which is the kilogram, time, which is the second as a unit associated with it. We have things like temperature. And as you may know, Kelvin is our kind of champion there in chemistry as our unit, and there's other things in terms of basic units. Now, when we look at the sort of units, really the SI system is kind of based off of the metric system, and we do use certain prefixes, right? And we use these prefixes to help us sort of change some of the meanings. Things like centi is 10 to the minus 2, kilo is 10 to the 3. Our friend nano, right, is 10 to the minus 9. So as we talked about it, it's really important. First off, this is basically 1 times 10 to the minus 2 written in scientific notation. That's 1 times 10 to the minus, or 10 to the 3. That's 1 times 10 to the minus 9, basically written in scientific notation. So it's very common that when people use these sort of prefixes, they oftentimes will do them backwards. So what you see here in terms of 10 to the minus 2 or 10 to the 3 or 10 to the minus 9, those are how much there is in the base unit to one of the prefix units. So for example, one that we've used before, in 1 nanometer, which is the prefix unit, there would be 10 to the minus 9 meters, or basically 1 times 10 to the minus 9 in scientific notation. It's very common. Again, people kind of do those conversions backwards all the time. Just like if I had 1 centimeter, there would be 10 to the minus 2 meters. So again, that is the proper way to use those things. It doesn't really matter the base unit. If I had 1 nanogram, I would have 10 to the minus 9 grams. So it doesn't really matter what the base unit is. The conversion works the same way. Just like if I had 1 centigram, that would be 10 to the minus 2 grams. So once again, it's a very common error that people make. They always want to kind of reverse those and go something like there's 10 to the minus 2 centimeters in a meter. And again, you want to watch out for that. You can also use sort of sometimes the larger sort of conversion of these guys by just dividing both sides by it. So for example, if we took our 1 centimeter is 10 to the minus 2 meters and divided 10 to the minus 2 are really 1 times 10 to the minus 2 to both sides. That gives us our same conversion of 100 centimeters is 1 meter, which sometimes people like to use maybe the bigger numbers than the scientific notation numbers. But if you do use scientific notation numbers, which is very commonly given to you in tables and stuff like that, you do want to make sure that you obviously use it correctly there. Any questions on that there? So speaking of scientific notation, let's talk about that, and to make sure, you know, everybody really understands how to use scientific notation correctly. So first off, when we write a number in scientific notation, it has the general formula of n times 10 to the n. And this number here does need to be a number between 1 and 10, so not 10, not less than 1, but it's got to be somewhere between 1 and 10. And the little n up here is either a positive or negative number, depending on really which way you need to move the decimal point, for example, to get it into a number between 1 and 10. So if I have something like 0.00256 and I want to turn that into scientific notation, I need to go 1 place to the right, 2 places, and 3 places, bless you, will give me a number of 2.56 times 10 to the minus 3. In this case, I move the decimal place to the right, and I have a negative exponent. If I had a larger number like 1, 2, 4, 5, we would assume the decimal point here is at the end. So 1, 2, 3 places will get me there. 1.245 times 10 to the 3 would be our number in scientific notation. So when we move the decimal place to the left, we have a positive exponent. The easy way to remember it is if you have a larger number, positive exponent, yes, smaller number, negative exponent. It is obviously opposite if you're going from scientific notation back to decimal. In the case of this guy, is positive 3, so we need to make it a bigger number. We got to go that way. And that's a negative 3. We need a smaller number, which means we need to go that way if we're going in the opposite direction. So do you have to write your numbers in scientific notation all the time? The answer clearly is no. But obviously, if the question asks you to give the answer in scientific notation, you should. And you should use proper scientific notation, which is this type of form here. Proper scientific notation is not 100 times 10 to the 3. That is not a number between 1 and 10. It's not like 0.93 times 10 to the 3. That, again, is not a number between 1 and 10. So to write a proper scientific notation, it does need to be, again, that number between 1 and 10. There are certain situations, as we will talk about in a second, that the only way to give your answer to the proper number of significant figures is to write it in scientific notation. And that is because when we see a number that's written in scientific notation, like our 2 numbers here, all of the numbers that come before the times 10 part, so all 4 of those and all 3 of those, are considered significant figures. So the number on the left there would have 4 significant figures. Number here on the right would have 3 significant figures. And that's why scientific notation is very useful in a sense, because let's just say the number on the right, I needed only 2 significant figures and not 3. So I could very easily just write it as 2.6 times 10 to the minus 3. Now I have 2 significant figures. If I needed just 1 significant figure, I could write 2 times 10 to the minus 3. Now I have 1 significant figure. So you can literally kind of control the number of significant figures by writing a number in scientific notation. And in certain cases, like I said, it's kind of the only way you could kind of get it to the right number of significant figures. Any questions on writing things in scientific notation? More importantly, right, just to make sure, our calculator and scientific notation, yeah. So every calculator is a scientific calculator, which you should have for this class, by the way, yes. has an exponent button. It is either an EE button. It is an EXP button. If you have some of the fancier new ones, yeah, times 10 to the n and a little will that's on your calculator, it probably is going to be like a two-tone version of a calculator with a different color on the outside and the middle kind of a different color. So these are really your exponent buttons that you want to use whenever you punch into your calculator a number in scientific notation. Other important numbers along the way is the negative number or change the sign number. That usually looks like that, or it looks like this on a calculator. You do not use the subtract button when you need to put a negative exponent in, otherwise you will get an error. So if we wanted to type a number, say like this guy up here, into our calculator properly, we should write type 2.56. You then should hit your exponent button, either your EE button or EXP button. On your display, it probably will look something like this, 2.56 and an E, or it may go like 2.56 and do like a little times 10 and put up a couple of zeros or something like that. When you hit this button right here, that represents the times 10 part of the number, which means you should not hit the multiplication button. You should not be hitting the second and log button or inverse log or anything like that if you would like to get the right answer in a lot of these questions that we do. What is left at this point is really just the negative exponent. And again, we want to use our negative button here and then 3, and that will go -3. It'll turn that into a negative and make that into a 3. And that is the proper way to punch into your calculator a number in scientific notation. Again, if you're using like the caret and the inverse log, you are doing it incorrectly, and you will find yourself with the wrong answer in a lot of cases because you're not putting it in correctly. Any questions on that? Now, if you have one of these calculators here, that has kind of the times 10 to the n and the little will, you do have to do a little extra work along the way here. And that's because typically the way these calculators are programmed, they're programmed pretty crappily. So what that means is you got to tell the calculator what you want to do. So when you have this set up as your exponent button, you need to actually open a parentheses first. You then need to put a 2.56 and then hit your exponent button. And when you do that on your display, you'll have a parentheses, a 2.56. It probably will do a times 10, and you'll have a little blinking cursor that's sitting up on top. At that point, you can do the rest of it. You could hit the negative button and 3. And what will happen when you do that is you'll have 2.56 times 10 to the -3, and then you'll have your little cursor button blinking next to it up on top. The problem with that is your cursor is up on top, and you actually need to close your parentheses. And in a lot of calculators, if you just close your parentheses with the cursor still up on top blinking, you'll get like a small little cursor closed there and probably an error on your calculator, depending on how it's programmed. So what you need to do at that point is you actually need to hit the will, and you need to hit that side of the will. And what that will do is bring your cursor down to a regular size cursor. And now you can close the parentheses at that point. And obviously you will end up with something that looks like this. So if you do have that calculator that has those buttons on it, not a big deal. You just got to kind of put parentheses around every single number that's in scientific notation. Otherwise, your calculator, based on how it's programmed, will most likely do the calculation wrong. It will separate the numbers incorrectly and do the math wrong. Any questions on how to properly put it into your calculator? Yeah. So let's just try one here. Let's take something like 6.25 times 10 to the -6, and let's divide it by 1.2 times 10 to the, let's do 17. I'll do it as well. Let's see here. Okay, let's take a look. So again, if you're going to punch this in properly into your calculator, again, if you have the times 10 to the n in the will, you need to put parentheses. But if you have the other buttons, you do something like this, 6.25, you hit your exponent button. You then hit your negative button and 6, then your divide button. your 1.2, once again, your exponent button, and just 17 in this case, and probably the equals button would be good as well. Once again, you don't see I'm doing any extra multiplication button or anything like that. So if we do this, we will end up with a number of something like 5.2 times 10 to the minus 23. On my calculator, I got 5.208333333 E minus 23. By the way, that's also a very common mistake people make when they punch it into their calculator. They forget about this part. That is this part. Yes. So you don't want to just put the front part of the number when it comes into your calculator. You also do not want to write your answer as 5.2 E minus 23. That is not proper scientific notation. That is shorthand for calculators in Excel. So when you give your answer, you do need to write it as times 10 to the minus 23. So make sure that you do write it that way. Any questions on that? So usually if you're punching these things in incorrectly, this part of the number looks good, that part not so much. It's off by a little bit there, and that's usually an indication that you are punching it into your calculator incorrectly. If you're not sure still where your exponent button is, just come see me at some point. We will figure it out together so that you know how to properly do it. But 100% in this class, you should always use the exponent button for anything scientific notation. And if you plan on going to 200B, you definitely should know where your exponent button is because you'll need it a lot when you go through there as well. But always make sure you do that. No inverse logs, no extra multiplications or anything weird like that. Any questions on, more importantly, the punch it into your calculator part? Yeah. All right, so now that we talked about punching into your calculator, let's talk officially about measurements, how to take proper measurements. Hope we know some of these things. So whenever we do take a measurement, there's always some degree of uncertainty. Right? So for example, if we take a ruler, we'll measure the classic arrow right about there. All right, so whenever we take any type of measurement, we should always look at the piece of equipment that we're using. And there's usually two types of markings that you can find usually on glassware. There's usually like a larger marking and a smaller marking. And it's really important to understand what does each of these represent. Usually the larger markings have the numbers, the smaller markings are the guys in between those numbers. So if we look at this particular scale here, we have a 1 and we have a 2, which means our large markings represent 1 centimeter. We also want to count the number of small markings there are between the two larger markings. And we always want to start counting past the first large marking and stop at the next large marking. So we would count here. That'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings between basically 1 centimeter. That means that each of the smaller markings in this case is how much? 0.1 centimeters, right? Is what each of those are. You get that by taking 1 divided by 10, by the way. Yes, there are 10 little markings. That means that this guy right here is 1.1, right? 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2 as we get over there. So when we take a reading, there should be always numbers that no matter who takes a peek at it, everybody should agree on pond. So when we look at my arrow, everybody should agree it is at least 1.4, right? Now, it is definitely not exactly 1.4, and it's not exactly 1.5. It's kind of somewhere in between those two. And that is where really the estimation comes into play, or the uncertainty in this measurement. Now, I may look at that and sort of break apart between those two markings, the 1.4 and the 1.5, and go, kind of looks halfway there. And I would record a 5 and also my units here, which would be centimeters. This would be all of my certain numbers. And this would be my first uncertain number. And whenever you take a reading, you should always record all the certain numbers and that first uncertain number. And what those two things are together is significant figures. Yeah. So that's really what significant figures are in a measurement, is all the certain numbers plus the first uncertain number. That would mean that this measurement here would have 3 significant figures in this particular case, right? So when we look at measurements and glassware, there are different scales. So we want to make sure that we always sort of look at the scale. So let's just say we have a 10 and 20, and these are milliliters. And we got a little curvature of our liquids put in there. And whenever we take a volume reading, right, we always read from my exaggerated meniscus, right? And the meniscus is the curvature of the liquid, and that's because the attractive forces between the liquid and the glass are actually stronger than the attractive forces between the liquid and itself. And on the edge, capillary action starts rising on the walls of the liquid, and you get this U shape. That's why when we take a reading, we always read from the bottom of the meniscus, because without that attractive force, the actual volume is down there at the bottom where it should be, because in the center, there is no kind of interaction with the walls of the container. So that's actually where you see it. So we always read from the bottom of the meniscus. Now, most things will have this sort of U-shaped meniscus. There are certain things that actually have a meniscus that goes in the opposite direction. And the most common one is mercury, which they've taken out of pretty much every lab. So you don't have to, you probably won't see it very often, but barometers used to be made out of mercury, and you would actually see the mercury go in the opposite direction. In this case, what's happening is the opposite effect. The attractive forces between mercury and itself is actually stronger than between the glass and mercury. So what happens is it kind of goes in on itself. So once again, in this case, we would actually read from the top of the meniscus, because that's actually where the volume actually would be. But probably 99 times out of 100, you're going to see the U-shaped meniscus as what's going to happen when you take a glassware. So in this case, we look at our large markings here, and that is 10 milliliter difference between the 2 big markings on our, wonderfully drawn graduate cylinder. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings between 10 milliliters. That means in this particular case, each of the small markings is 1 milliliter, right? And that would be 11, that would be 12, that would be 13, 14, 15, 16, 17. We'll just say my meniscus is somewhere in that ballpark there. So once again, if we were going to take a reading at this point, it would definitely be at least 15. And again, maybe in this case, you feel it's actually a lot closer to the 15 than the 16 marking. It doesn't always have to be a 5 at the end. You can, write something like 3, right, milliliters. And once again, this would be our certain numbers. This would be our uncertain number. And once again, that would mean that this guy also would have 3 significant figures. So usually it's assumed kind of plus or minus 1 of the last digit, right, is sort of where the error might be. Any questions on taking proper readings there? By the way, you should always look at the scale, because, maybe you got something going on like this. And we'll put our meniscus somewhere in that ballpark. So in this case, our large marking is 10 milliliters. We now have 1, 2, 3, 4, and 5 markings between that. In this case, each of the small markings would then represent how much? 2 milliliters, right? So that's going to be a 12, a 14, a 16, and an 18. Now, when my meniscus falls right there, I am now between 14 and 16 in this case. What comes between 14 and 16? 15 does come between 14 and 16. And that would actually be the best you could do in this case, right? That would mean this measurement would have how many significant figures? Two significant figures. The uncertain or estimated digit would be which one? It would be the 5, right? And that's where we are. Because the spread on this particular one is 2 milliliters, there's no way to know in your head where 14 stops, right? 15 begins, and so forth. There's not enough room to do that. When there's only like a 1 unit difference, you could kind of equally divide it up and kind of figure out, is it halfway? Is it more? So in this case, the best way we could do is actually take it to the whole number. In most cases, when you take a measurement, you typically can take the measurement to one more place to the right of the smallest marking. So what that means is our smallest marking on our ruler here was the first decimal place. We're able to go one more place to the right and take the reading. Our smallest marking on our graduated cylinder in this case was 1 milliliter. We're able to go one more place to the right and take a reading. By the way, if you're not sure how far you should ever take a reading, but you know how to figure out what the smallest markings represent, you can just take the smallest markings and divide it by 2, and you get something like 0.05. That's 2 decimal places. That's how far you should take the reading. You divide this guy by 2, you get 0.5. That's 1 decimal place. That's how far you should take the reading. Even works with this guy. If I divide this by 2, I get 1 milliliter. That's as far as you should take that reading too. So if you're not really sure, how far you should take it, in general, one more place to the right of the smallest marking. But again, if you could figure out what the smallest markings represent in terms of value, you could divide it by 2, and basically that'll tell you how far you can take the reading to. Any questions on that there? One last thing about measurements here is, again, if we had our same ruler setup that we had previously there, and let's just say we're like right about there. So just like last time, our large marking is 1 centimeter. Our smaller marking is 0.1 centimeter. So that's 1.1, 1.2, 1.3. So let's just say we feel it's a dead on 1.3 marking. If I record 1.3 centimeters, 1.30 centimeters, 1.300000 centimeters. That feels like a lot of zeros. Too many zeros, perhaps. Yes. So adding zeros not good in some cases, right? Is there a difference between if I said the measurement was 1.3 or 1.30? There is a difference, and it does matter. So in this case, what we're saying, if we look at these two different measurements, are this number would have 2 significant figures, right? Which means the uncertain digit is the 3 here, right? So what you're saying when you write 1.3 is, I think it's 1.3 centimeters, but maybe it's like 1.4, maybe it's 1.2. That's where the error is, right? That's a pretty big range of error if we look at our actual ruler, and it's actually nowhere near that range of error, right? So we actually just made our measurement a lot crappier by taking off that 0 that actually should be there. So we wouldn't want to do this. This guy here would have how many significant figures? 3. The uncertain number would be the 0, which means we're saying, I think it's 1.3 centimeters, but maybe it's 1.31, or maybe it's like 1.29, which is more realistic to what we're seeing there on the actual scale. So even if you hit dead on a number, you don't want to lop off like a 0 or anything like that. You want to maintain the proper number of significant figures when you take a measurement. Otherwise, you just made your measurement pretty crappy. Yes, a much more error inputted into your measurement that really shouldn't be there. Any questions on that there? Also goes with things like digital readings. Yeah, that's also a very common place where people just like forget numbers. So if you have a digital display, like on your balance, all the numbers are important. Otherwise, they would not be there. So you should always record all the numbers on a display. Any questions on a properly taken measurements? Yeah. Okay. Now, when we take measurements, there is accuracy, right? And precision. And there is a difference between being, say, accurate and precise. Being accurate means that you are close to the true value. I'll maybe write that. When you're precise, or you look at precision, or you're precise, you are looking at a group of numbers are close to one another. So, for example, the classic example of throwing some darts at the bullseye, right? The goal there is to hit the bullseye. So I take my 3 darts, I toss them up there, I hit there, I hit there. Okay, well, maybe I missed the board. It happens. Am I accurate? No. Am I precise? Not so much. I missed the board. The board was moving. There was wind. It happens. So I go, all right, let's double or nothing it up in a friendly, non-wagering type of situation. And I lay out my darts and I go boom, boom, and boom. Am I accurate? Am I precise? I'm precisely not accurate, right? So you can be very precise, right? And you can repeat something wrong every single time because that's just the way you do it, right? And you can be very, very precise, but not very accurate, which obviously is not what we're looking for. Now I go triple or nothing here. Get rid of my darts, pick up my darts, and I lay my darts in there. And boom, boom, boom. Am I accurate? Am I precise? Yeah. So when we do measurements and we do experiments, right, we want to be both of those things. We want to be both accurate and precise, which is why in a lot of experiments we do multiple trials, right, to see if it's reproducible, right, if we could get the same answer every time that we do it. In terms of accuracy and precision, we sometimes look at different things. For accuracy, percent error is very commonly what we look at, and percent error is your experimental value minus the true value divided by the true value times 100%. Here at this school, they have you take the absolute value in a lot of these calculations. If you don't take the absolute value, it's possible to get a negative or positive number for percent error. Positive number means you're a little above the real value. Negative number means you missed it on the low side, but you can get that. But here they typically will have you do something like take the absolute value. Precision, we could look at standard deviation, or percent standard deviation, which is like your standard deviation divided by your average times 100%. We'll give you that. Standard deviation is the sum of each individual value minus the average squared divided by n minus 1. Not that we calculate standard deviation very much in here at all, but that's how you calculate it. So a lot of times we look at standard deviation, how much the numbers sort of vary from each other. You could also look at percent deviation by using just the average. So you could take each individual number minus the average divided by the average times it by 100, and I'll give you some deviation in percentage. So when we look at precision, we look at deviation a lot of times. When we look at accuracy, we look at percent error. Percent error, you want a low number, right? A low number is good. That means you're very close to the true value. If you have a percent error of 200%, then you did it twice as wrong as the person next to you. Now you did a lot of bad, but you're not very close to the true value. Any questions on accuracy versus precision here? Okay, so let's talk a little about officially significant figures now that we kind of know where they come from. So the way that we count sig figs, as you hopefully know, any number that is a non-zero number is significant. So if we have 2, 3, 4, we always start counting left to right when we're doing significant figures. We always start at the first non-zero. So this guy would have 3 significant figures. Then we have zeros, and there's a few different types of zeros that we come across. There are what are sometimes referred to as leading zeros, and those are not significant. So 0.00422, none of these are significant. We do not start counting until we hit the 4, and then the rest of them are non-zero. So this would have 3 significant figures as well. There's also trapped zeros, are sometimes referred to as captive zeros. Those are significant. The 4004 We start counting here. These guys are significant and that guy's significant. So this would have 4 significant figures. The 0 at the end, which is the trailing 0, sometimes referred to, is the one that gives people the hardest time. And those zeros at the end may or may not be significant. And what determines whether or not they are significant is if there is a decimal place point anywhere in the number. Then all those zeros that come out at the end will be significant. If there is not a decimal point, then those numbers, zeros at the end, will not be significant. So if I write this 600, how many significant figures does it have? It has only 1, which would be this one right here, right? Now, if I write 600 like this, how many significant figures does it have? It has 3, and these guys at the end would be significant because of that 0. If I had 0.00200400300, how many significant figures is that? I have no idea. It's just writing numbers. So let's see. We're going this way. We're not going to start counting really until we hit the 2, right? These are traps, so they're significant. That's significant. These are still traps, so they're significant. That is significant. So these zeros at the end, are they significant? The answer is they are significant because way over here, there's a decimal point. So the decimal point does not need to be near the zeros at the end. They just need to be anywhere in that number. I have no idea how many that is now. 2, 4, 6, 8, 9, 6 figs, I think. I'm not counting now. So sometimes people also will make a mistake and think something like this, like these zeros are significant because they come after the decimal point. And that's not the case because we would not start counting significant figures until we hit the 4. Yeah. So until we hit the 4 is where we would start counting our significant figures. And then the 2 and the 3 would be significant. And that would give us 3 significant figures in this particular case. Now, when we talk about, say, a number like this, which is 12,000, right? How many significant figures does it have? It does have 2. Which one is the uncertain or estimated digit? It is the 2, yeah? So not all the time is the estimated digit or the uncertain digit the last one written. It is a lot of times it is the last one written, but it always is the last significant figure that you have on the page. So it may not always be the last one written, but it definitely is always the last significant figure. Any question on that there? By the way, if I wanted 3 significant figures and I want to write this number with 3 significant figures, can I do it in like decimal form here? Would something like this be 3 significant figures? Should I write it like that? I should not, because there's a very big difference, right, in the meaning of 12,000 and 120. If I owed you $12,000 and said, here's 3 significant figures, here's $120, might not make it out of the room. You look friendly, maybe I will. But we never want to, speaking of rounding, right, which is also a very common mistake that people make, we never want to do extreme rounding where we change the meaning of the number, right? So in a case like this, if we wanted 3 significant figures, the only way to do it is a little scientific notation action, right? So we go 1, 2, 3, 4. That gives me 3 significant figures. It maintains what the value is, and that would be the proper way to do it. So that's what we were talking about earlier, that in some cases, the only way to give it to the right number of sig figs is to write in scientific notation. And speaking of rounding, normal rounding rules apply, right? Above 5 there, 5 or above, we round up, and anything less, we drop off along the way. Now, speaking of calculations with significant figures, there's basically 2 things that we do, which is multiply and divide, or add and subtract. When we multiply or divide, our answer should have the same significant figures as the number with the least number of sig figs. So if we took 425 and times it by 1.2, that is 3 significant figures. That is 2 significant figures, which means my answer should end up with 2 significant figures when it's all said and done. When we add and subtract, our answer should have the same number of decimal places as the number with the least number of decimal places. So if I take 1.111 and I add it to 2.22 and add it to 3.3 and try without the calculator, 1, 3, 5, 6, 3, 5, 6, something like that. Here we're going to look at decimal places. That's 3 decimal places. That's 2. That's 1, which means my answer should end up at 6.6, which has 1 decimal place, but 2 significant figures, right? So that's also important. If you do multiple steps together, you need to keep track of your significant figures. So if we did something like 1.2 times 333 divided by 4, and then we added 0.32 to it, right? We're doing a lot of different things at once, right? We would normally start here at the multiplication part in our parentheses. So that is 2 significant figures. That is 3 significant figures, which means technically when we get the answer from the top, we should end up with 2 significant figures, right? The next thing we would do would be dividing. We would take 2 significant figures divided by the bottom, which is 4 significant figures, which means our answer for this part should actually be 2 significant figures in this case, right? So if I put this in my calculator, I got 1.2 times 3.333 divided by 4, creative numbers there. And on my calculator at this point, I got 0.089918992. And now we're going to add this to this number, basically, right? So if you wanted to, you could round at this point the first number. You could add the next number if you wanted to, and you'll end up with something like 0.409918992. Now, 2 significant figures on our first calculation really should take us to here, right? Which means this is a 9, which means really this should round to really 0.090, right? We are now doing in our very last step here addition. And then the smallest number of decimal places is now 2 decimal places and 3 decimal places, which means we really should end up right about there at 2 decimal places, which would be actually right about there. And we have to look at this number, and we should end up with something like 0.41. So when you're doing multiple steps in a calculation, you really shouldn't round until the very end, but you do need to keep track of everything that you're doing and kind of clean it up at the end. The reason we don't want to round along the way is if we round along the way, every time we get the answer and we round, we are moving ourselves probably further and further away from the correct number in that situation. Any questions on that move right there? No. All right, so multiplying, dividing, adding, subtracting. No. Yeah. It works the same. So for example, I think you're asking if you're like say multiplying something, is that what you're asking? Something like this, and say you multiplied it by something like this. So if we did this again, we would put it into our calculator using our exponent button 1.25, exponent button -3 times 3.2, exponent button 4. I think it's me 40. What a random number I chose there. We'll try that again. 1.25 exponent -3. All right, 3.2 to the 4. We'll make it work. Oh, you got 40 on the nose there. Good pick of numbers, I suppose. Now, we're still multiplying. So here we would want to look at significant figures. And because this is written in scientific notation, this guy has how many significant figures? 3. This guy has 2, which means this answer should have 2 significant figures. Is the way I wrote it 2 significant figures? The way I wrote it is one significant figure, right? So I could lay up a decimal point there, and then it would be two significant figures. If I wrote it like this, would it be two significant figures? It would be three significant figures, actually, in this case, as all those zeros would be significant, which would be too many in this case. So the other way you could do it is a little 4.0 times 10 to the 1, right? Which would also give you two significant figures if you wrote it in scientific notation. So you would follow the same steps, the same rules. And just because it's written in scientific notation, you already know what the sig figs are for those guys. Now, the reason we choose the least in each of those cases is because your measurement or your calculation is only as good as your crappiest measurement. Yeah. And your crappiest measurement will have the least number of significant figures or the least number of decimal places. So that's really the thing that limits how good your calculation is, and really how good your overall measurement is really your worst piece of equipment that you made the measurement with. Any questions on that there? Okay, so that is that. Let's talk a little bit about then temperature conversions, just to make sure. When we do temperature conversions, there's really three types of temperature scales. There's degrees Celsius, degrees Fahrenheit, and Kelvin. The main difference is Kelvin is the one we use the most, and there is no degree, so it is just Kelvin. The difference between all three of these is where water freezes on these scales. So if you want the temperature in Fahrenheit, that is 1.8, the temperature in Celsius plus a 32. If you want the temperature in Celsius and you have Fahrenheit, temperature in Fahrenheit minus 32 divided by 1.8. 1.8 is 9/5, which is like the fraction some people have learned to do these conversions. So you get the same thing. And that will give you your temperature going from Fahrenheit to Celsius or Celsius to Fahrenheit. Most commonly, though, we go Celsius to Kelvin pretty much mainly here in chemistry. And to do that, we take the temperature in Kelvin is temperature in Celsius plus 273. The proper number is 273.15, but most people don't use the 0.15. If you like it, you can use it. But oftentimes we'll get kind of rounded off. So 273 is pretty good anyways. And obviously going the other way, Kelvin to degrees Celsius, temperature in Celsius would be our Kelvin minus 273. So out of all these, pretty much that is the mainstay, and this one as well. But pretty much if it is chemistry, if it has something to do with temperature, if it is a formula that has temperature in it, you probably best just convert it to Kelvin. And that's even if you have problems where they give it to you in Celsius and ask you to give the answer in Celsius. In those cases, when you go into the formula, you got to convert it to Kelvin and then back to Celsius on the back end. So definitely the Celsius to the 273 plus the 273, you do need to know. We use it a lot in chemistry, obviously. Any questions on that there? Now, let's talk about equalities. Like we got 5,280 feet is equal to 1 mile. That is what is referred to as an equality. And an equality is two things that represent the same amount, but are on different scales, like 100 pennies, right, is equal to $1. And from any equality, we could write two conversion factors. And that is 5,280 feet over 1 mile. Our 1 mile is 5,280 feet. We use conversion factors when we do problems, what is referred to as problem solving, or more importantly referred to as dimensional analysis. And typically in chemistry, dimensional analysis is the way that they want you to show your work when you solve problems. And the basic idea of dimensional analysis is conversion factors and unit conversions. So if you have a specific unit that you want to get rid of, you use a conversion factor and you put that unit in the opposite location so it will cancel, and you put the unit you want in the other location. So unit A and unit A will cancel, and that will give you unit B. What we're doing mathematically is multiplying whatever's on top and dividing by whatever's on the bottom. So when unit A is on top and unit A is on the bottom is the same thing as you divided 2 divided by 2, that equals 1. So those units cancel out that way. So if we had something like we walked 400 miles, yes, and we wanted to know, I'll put a decimal point there, how many feet that was. We would set this up with 400 miles, and we would want to use a conversion factor where we see the opposite there. So miles are on the bottom and feet are up on top. And miles will cancel. We're going to multiply across the top there. It's going to give us 400 times 5280. Gives us something like 2112000 feet in this case. Now, in terms of significant figures, we do want to keep track of what we're doing. This is a conversion factor, and it is referred to really as an exact number. And you might be familiar with exact numbers, but just in case you're not, an exact number is basically one of two things in chemistry. It is, if you, for example, had some pins out here on my desk, I'm not going to do any type of experiment to figure out how many pins I got. I'm just going to count basically how many pins I have. So anything that's achieved through counting is considered an exact number. Any type of equality or definition is considered an exact number. Now, there is an exception to that, and that is it's an exact number if you have a metric to metric conversion. So that's considered an exact number. You don't have to worry about it. If it is an English to English conversion, you don't have to worry about it. But technically speaking, if you cross over from metric to English, that is not considered an exact number, and you should look at it when you're doing a calculation. So, for example, if you had, say, 946 milliliters is a quart. Milliliters is metric, and quarts is English, and that is a crossover. If we were to use this as a conversion factor, like 946 milliliters over 1 quart, our 1 quart is 946 milliliters. We would look at this as having 3 significant figures in our calculation. Now, if it's an exact number, it basically means that you could have as many significant figures as you want. And what that means in calculations is we just ignore it. We don't actually look at it. So in this case, we would actually ignore this. And the only number that has significant figures here would be this number that has 3 significant figures, which means I should end right about there. And maybe a scientific notation would be in order in this case. So 1, 2, 3, 4, 5, 6 places. And this would give me my proper number of significant figures in this particular case. Now, there are a couple of conversions that's metric to English, which is considered an exact conversion. The most common one is 1 inch is 2.54 centimeters. So if you come across that, that is metric to English, and that is an exact conversion. So you would not have to include it or worry about it. I would say probably 9 times out of 10, but not 100 times. But 9 times out of 10 or 99 times out of 100, a lot of times that first number, if you're just doing a conversion, usually will have the right number of significant figures or pretty close to the right number of significant figures as your answer should have. Any questions on dimensional analysis? So again, that is what you're supposed to show. So for example, if I had 335 cubic inches, how many cubic feet would that be, by the way? So why don't you take a moment there? We hopefully know 12 inches is 1 foot. What would the answer be with the proper number of significant figures? I'll do it as well. Let's see if we can. Yeah, let's take a look at this. So again, we're going to take 335 cubic inches. And we can use our conversion factor here to go from 12 inches as 1 foot. Our 1 foot is 12 inches. So we want to go opposites here. So we'll put inches on the bottom. So we'll use the guy on the right there. 12 inches is 1 foot. If I do that, did I completely change what I needed? No, because this is only one of them, right? So I actually need to do this not once, not twice, but actually 3 times to get the proper units here. 1 inch, 2 inches, 3 inches is inches cubed. They all cancel. Then we're going to multiply across the top. So everything that's on top gets multiplied, which in this case is all ones, and we'll divide by the bottom here. Divide. So that would give us 335 divided by 12. By the way, I would hit equals. Divided by 12, I would hit equals. And then divide by 12 again and hit equals. Very common mistake people make is they want to punch everything into their calculator all at once. And if you do not know what you are doing in terms of parentheses, you will oftentimes get the wrong answer. You will never get the wrong answer usually if you do it correctly. You can multiply as many numbers as you want on top. And then for every number that's on the bottom, you should hit equals and divide equals, and you'll always get the right answer. By the way, my units here are feet times feet times feet, which is a cubic feet. Significant figure wise, this is an exact conversion, which means 3 significant figures should end there. 0.19 need to round up, gives me cubic feet. Yeah. Any questions on that? Now you can do it where you just, put the cube up there on the first one if you like. But in my experience, people will put the cube up there and never live to actually do the math. So sometimes it's better just to write it out. Can't tell you how many tests I've seen where people don't do that, but they have it written, but never actually punch it in correctly. By the way, I got like a cubic foot, right? Cubic feet is a what type of measurement? Length, volume? It is volume, yeah. So when you take a length measurement and you cube it, it is a volume, right? That is why we have something like cubic centimeters is the same thing as a milliliter, right? Also 1 cc, which is also a cubic centimeter. We get a cubic centimeter by basically taking 3 length measurements, right? And if we take the length times the width times the height, all measured in centimeters, gives us a cubic centimeter, which is a volume. And that's a very common way that we can calculate the volume, like of a square or a cube or something like that. That's a solid. Take a ruler out and take those measurements and stuff like that. By the way, speaking of volume, common conversion factor, 1,000 milliliters is 1 liter. Yes, we use that a ton in chemistry. Any questions on conversions, dimensional analysis? Yeah. So you got like 2 units going on? Yeah. Okay, so we'll do a different one. So I'm not doing the study assignment, but we'll do let's say we got like miles per hour, right? And we're driving a nice conservative 55, right? There we go. And we're driving 55 miles per hour, and it's important to set it up as dimensional analysis where you can see both units. And sometimes we do have units on top and units on the bottom that you could kind of see where they're located. Sometimes when people do what I call stacking the units, where they don't show a dimensional analysis, they kind of write miles and slash hours, and then you do the next one with all the units next to it. They lose track of like, should I be dividing? Should I be multiplying? So if you set these things up with dimensional analysis, you could clearly see what you should be doing mathematically, and it makes it easier. So we need a pathway. Say we want to go to, say, I don't know, we want to go to like meters per second or something like that, right? And if we want to go from miles per hour to meters per second, we basically have 2 conversions we need to do. We need a pathway to go from miles to meters, and we need a pathway to go from hours to seconds. And by the way, there are multiple ways you can do this depending on what conversion you choose, what pathway you choose. So for example, let's just do in 1 kilometer, there is 0.621 miles. So we could use this to go from miles to kilometers. We know that kilo is 10 to the 3, which means we could use that to go from kilometers to meters. And there would be 10 to the 3 meters in 1 kilometer. So that will get us our top path to where we need to go. Bottom path, right? There's something like 60 seconds in a minute, I hope. And there are 60 minutes in an hour, right? So that again is our pathway that we can use for the bottom. So by setting this up like this, 55 miles per hour, I'm going to start with the miles. So on the bottom, I want miles, so it cancels. So we'll go 0.621 miles is 1 kilometer. If I stop the calculation right at this point, the miles would cancel. And the units that I have are kilometers on top, hours on the bottom, right? Which is close to what I want, but I need to get it down to meters. So by setting it up like this, I could clearly see that kilometers are up on top. And to get rid of it, I need to go opposite, which means I want to put my 1 kilometer on the bottom, my 10 to the 3 meters up on top, which again is 1 times 10 to the 3. And kilometers and kilometers would cancel. If I laid up right here, I have meters on top, which is what I want. I still have hours on the bottom. So now I really took care of the top part of the conversion. Now it should work on the bottom. And this is why it's important to set it up like this. I could clearly see the hours are on the bottom, which means to get rid of them, I need to go opposite and put it on top. And again, people will very commonly screw that up, multiply when they should divide or divide when they should multiply. So we're going to go up on top. 1 hour is 60 minutes. If I cancel now, hours and hours will cancel. Units I'm in at this moment are meters up on top and minutes on the bottom. So I'm really close to what I want. I got to go one more spot, and I'm going to erase what I got in my way here. But we have minutes on the bottom, which means we want to get rid of it. So once again, up on top is going to go minutes, and 1 minute. There is 60 seconds. Minutes will cancel. Units I'm left with now are meters up on top, seconds on the bottom, which is what I'm looking for. And again, I'm going to multiply everything that's on top, which is basically 55 times 1 times 10 to the 3. We're going to come back and divide by 0.621, hit equals, divide by 60, hit equals, divide by 60, hit equals. And that will get us 24.6 meters per second as our answer that we would get here. Yes. I did on my calculator, I hope. Let me double check, but I believe I did. So we got 55 times 10 to the 3, which takes care of the top part, right? We're going to come back and divide by 0.621, hit equals, and divide by 60 and hit equals, and one more 60, hit equals 24.6. Now let's talk sig figs. Did I give the answer to right sig figs? Not so much, right? We don't have to worry about this one. We don't have to worry about that one or that one because they're all exact numbers. That's a metric to English crossover, which means we really have 3 significant figures based off of that number. The one you ignore, but the other number you look at. This one actually has 2, which means really I should end up here at 25 meters per second will be my proper number of significant figures in this case. Any questions on that? So you should show your work with dimensional analysis in this class and all the chemistry classes you take. It also benefits you in 2 ways. You can make sure that you're doing the math correctly, which again, when people have something like that where they have 2 units, they're not sure like what they should do with that second unit. Should they be multiplying or dividing? So it helps you with the math part. It also, in a lot of cases, when you think about chemical formulas that we learn or formula or equations that we learn throughout the semester, they're mainly just conversions. So you could almost take a dimensional analysis approach to a lot of calculations that involve formulas and just think about what units you need to get rid of and what units you need to end with. And a lot of times you can almost do the math without knowing the formula if you kind of set up the units so that they cancel correctly. So it's a really beneficial way you should do it. And as a chemistry instructor, I suppose I should say that is the way you should do it in here in your other chemistry classes as well. Any questions on conversions, dimensional analysis, significant figures, any of those things? Right. The last thing I think we're going to talk about, I think I might have covered everything, is density, just to make sure, right? So density is defined as the mass of a substance over its volume, and density typically has some units, and those units are usually grams per milliliter or grams per cubic centimeter. And as we just talked about, 1 milliliter is the same as a cubic centimeter. And these are the typical units that we see for density for things that are solids and liquids. Now, when we get to gases, you will usually have density units of grams per liter. And that's usually what we see for gases. And we'll see that actually in the gas chapter when we get there. So the formula for density is mass divided by volume, which means that volume would equal mass divided by density, and mass would equal volume times density. Sometimes people remember the DMV triangle. Yes. Density is mass over volume, volume is mass over density, and mass is density times volume. If something is more dense than water, it will sink, right? And if something is less dense than water, it will float. Most substances in their solid form is usually more dense than their liquid form. The major exception to that is water, right? Water in a solid form is actually less dense than its liquid form. We know that because when we get a nice refreshing drink and we put ice in it, ice ends up on top floating, right? And that's because water is unusual in the fact that when a bunch of water molecules come together when they are freezing, because of the hydrogen bonding, they actually can't get super close to each other, and they create a lot of empty space between the different water molecules. And if we think about density formula, that means that we're kind of bloated our ice, and we have a much larger volume than we do, say, in the liquid form. And that means a larger number on the bottom when we divide it will give us a smaller density. So actually ice and water is unusual in that sense because ice actually has a lower density than liquid water. And most things are sort of opposite than that. So when we do density in terms of the volume, there's really a few different ways that we can get the volume. We obviously can fill a graduated cylinder or something like that and just take a volume reading. We could do what we just talked about a second ago. If it's like a solid cube, take the length times the width times the height and get something like a cubic centimeter, which is a volume. The third way, which is very common with density, is we could do volume by displacement. So if we fill up something like a graduated cylinder with a certain amount of volume, and if we take a solid object and we drop it inside, what's going to happen is your graduated cylinder will change shape and the solid object will now be in there. And the volume will be displaced by that solid. The solid will actually displace a volume that's equal to its own volume. So if you take the difference in the volume here, that is your volume of your object, is your final volume minus your initial volume. So for example, if this started at 25 milliliters and it ended at 30 milliliters, and we put in there this thing that weighed about 52 grams. When we do our density here, we would take the volume of our object would be our final volume, which is 30 milliliters minus 25 milliliters, gives me 5.0 milliliters. Our density here would be 52.0 grams divided by 5 milliliters. That's going to give me 52 divided by 5. 10.4. The units do not cancel, so the number always stays with the grams part. It's always 1 milliliter. By the way, how many significant figures should I end up with in this case? It is 2 based off of this calculation, right? Here we were going to decimal places, which is 1 decimal place, but this number has 2 significant figures. Last thing we did is divide. That is 4 significant figures by 2 significant figures. which means I should end up with 2 significant figures here, which would be something like that, perhaps. Yeah. So when you do something like this, again, you want to kind of follow your calculation through to figure out, and it's obviously the volume calculation that limits our density value here. Any questions on that there? By the way, if we have a density given to us, like the density of a substance is 1.25 grams per milliliter, and we have 35 grams of it, and we want to know the volume. We could also, like I was saying before, you can use the density equation, which is mass over volume. You clearly have density given to you. You got the mass. You could rearrange and solve for volume, which is mass divided by density. But as I was mentioning before, where dimensional analysis can be very helpful is, maybe you're not so sure you rearrange this correctly or not. You could use something like density as a conversion factor, or you could say something like 1.25 grams per milliliter, or a milliliter is 1.25 grams. And I know I have 35 grams. So I do know I want to get rid of 35 grams and figure out the volume. So you could actually just approach it like a dimensional analysis problem and go, all right, I need to get rid of the grams. So I want to do this move. And without really knowing properly how to rearrange that equation, if you know how to do dimensional analysis, you now know you should be dividing, which is the correct thing that you should be doing. You could see the units cancel and know, okay, I need a volume that gives me the milliliters without even really knowing the density equation. And I could just take the 35 divided by 1.25, gets me 28 milliliters as the only unit left over. And in this case, sig fig wise, that is 3 significant figures. That is 2, which I got lucky there. And that ends up as 2 significant figures in this case. So you definitely could use something like density as a conversion factor. And like I said, if you get into the habit sort of setting up your problems in that dimensional analysis approach, it kind of makes a lot of things easier. Any questions on density? By the way, if I put different density liquids together, which layer is the most dense? Most dense layer is the bottom layer, right? Least dense would be at the top. If I put some solid in there, that means that solid is more dense than what's above it, right? And less dense than what's below it, right? So you could kind of figure that type of thing out. All right, any questions on any of this kind of pre-chemistry stuff? Again, it's in that pre-chapter. You are responsible for it. And it will be some questions on all this stuff on exam 2, and it is the study assignment that is for today's lab. Any questions?